In this video, I'm going to be covering section 4-2b, the multiplication rule of probability. So in the prior video, we looked at the addition rule of probability. And the addition rule of probability is used when we were dealing with OR probabilities in a single trial, whereas the multiplication rule is dealing with AND probabilities in multiple trials. So before we get started, let's go ahead and take a look at this pre-skill. So with the multiplication rule of probabilities, you have to be familiar with multiplying fractions, either using the calculator or just in general multiplying fractions, right? So for the first one, anytime you're multiplying fractions, the way that we multiply fractions is we multiply straight across, right? We multiply the numerators with the numerators, and then that's going to be the new numerators, or the answer to the numerator for the fraction. And then we're going to multiply straight across the denominator, and that's going to be the answer for the denominator, the product of the denominators, right? So using the TI-84 calculator, here's a handy way you can do this. So what you can do is, you know that in the numerator, it's the product of the numerators here, and then in the denominator, you have the products of the denominators, right? So you have a couple ways you can do this. You can then, if you realize that, you can open up parentheses and then just do the multiplication of the numerators, and then close parentheses, and then by doing that, you know that that's going to be the product of the numerator, or the numerator is the product of all of these numerators, and then you can divide, so indicating that that's what you're going to input now is the denominator, right? So we're going to open up parentheses, and we're just going to put the product of the denominators down there. Oops. Okay, multiply. And then we have that. And then close parentheses. Press enter. And we get this answer. So if you guys remember by watching my prior videos on using the TI-84 calculator, this notation, this is scientific notation for the following, right? So this e to the negative 4 tells me that I'm going to move this decimal point 4 times to the left. So what I have here is I have 1.40696 ... e to the negative 4. So essentially what I'm doing is I'm dividing by 1,000. So that's 1 followed by, I'm sorry, 10,000, because that's going to be 1 followed by 4 zeros. If you don't remember that, just know that what you're doing here is you're going to move the decimal point 1, 2, 3, 4 times to the left, and then fill in those empty place values where you jumped over, where you jumped over to the left here with empties with zeros. Okay, and then the instruction says to round to 4 decimal places, so we know that this is the 4th decimal place, and rounding to 4 decimal places, this is going to be approximately 0.0001. Okay, moving on to the next one. So the next problem, number 2, you can definitely do the same thing. You can do the following. You can open up parentheses and then do 28 times 28 times 28 times 28 times 28 5 times, right? And then close parentheses and then the division sign, and then open up parentheses and then multiply the denominator like that, or that's what you get in the denominator, and then close it and press enter, and then that's what you get, right? So very similarly, we're going to move this decimal point 4 times to the left, which means we're going to jump to the left over the 1, right, or under the 1, and then do it 3 more times. So what you're going to end up with is 0.123 zeros, and then the 1, and the 9, 2, 3, and then ... right? And then we know we're going to round to the 4th decimal place, so we're going to get approximately 0.0002. Now, alternatively, whenever you have repeated multiplication of the same number, right? Repeated multiplication of the same number. We know that we can write this or evaluate this like using exponents. So this is equal to 28 over 155 raised to the 1, 2, 3, 4, 5, so raised to the 5th power. So if you work that out, again, it's a little bit, it saves you some time rather than doing what I did here. It saves you a little time, right? You can open up parentheses and then do 28 over 155, close parentheses, and then raise that to the 5th power. So the power function is the caret button right here, right above the division sign. So we're going to raise that to the 5th power and then evaluate. So notice how we get the same exact answer. So it's a little of a shortcut that you can use. Saves you a lot of time as you're going through these problems. Okay, so as mentioned when the video started, multiplication rule is used with and probabilities in multiple trials. Now, what do I mean by that? So whenever you're trying to find the probability of event A and then event B in the second trial occurring, and then event C in the third trial occurring, and so on, that's what we called an and probabilities in multiple trials, because there's more than one trial. Whereas with the addition rule, it was just one trial, meaning if we were making a random selection, we were just selecting one person or one item, and that we were looking at probabilities of A or B, right? We're looking at probabilities that one item is either A or B. And multiplication rule is with and. And so because of that, because of the multiple trials, we have to consider whether events are independent or dependent of each other. So all that means is the following. So two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. So if two events occurring doesn't affect the probability of one or the other, or let me just rephrase that. So if A occurs and that does and then B occurs and event A doesn't affect the probability of event B, then we say that the two events are independent, and vice versa. If B occurs and then that by B occurring it doesn't affect the probability of A, then we say that the two events are independent. If they're not independent, then we say they are dependent. So the notation we're going to use here is the probability of A and B. And again, well, that notation means the probability of A occurring in the first trial, then B occurring in the second trial. So again, we're dealing with multiple trials, right? More than one trial. The second notation is read as the following. So anytime you see the probability P and then B with a straight line and then A, this is read as the probability of B occurring. So the probability of B occurring given, so that straight line is read as given, that A has already occurred. So essentially the way that we read this would be the probability, right? That P stands for the probability of B occurring given that A has already occurred. All right. So the multiplication rule of probability is the following. So we have two formulas. The first one is the general formula. You can use it anytime. Whereas the second one is for independent events. And it'll make a little bit more sense when we actually do it. This is the general one where you can use it anytime. This one is primarily it's looked at or used when you have independent events where the two events don't change or affect the probability of the other. Okay, so let's take a look at this one example. So we have a math instructor is randomly selecting students from his 4 classes to receive extra credit towards the next exam. So we have this instructor, she's randomly selecting students from 4 classes and to get extra credit. So the number of students in each class is listed to the right. Find the probability of each situation. So in class 1, we have 45 and then 50 in the next one, and then so on, right? So for a total of 155 students in all 4 classes. So the first question says, find the probability of selecting 2 students from class 3. Assume the selections are made without replacement. So here's a hint, or like a note, important note that you want to take down. Anytime you have selections with replacement, that implies that we have independent, the 2 events or the events are independent of each other. And whenever it's without replacement, we have dependent events. Now, sometimes some problems are going to explicitly say with replacement or without replacement, but sometimes you're going to have to read into the problem and understand the situation and decipher whether it's with replacement or if it's without replacement. So in this problem, it says without replacement. So here we have the problem is essentially the probability of that the first student is from class 3. So let's just write down C3 from class 3. And then the second selection is class 3 as well. And because it's without replacement, it's going to change the first event is going to have an effect on the probability of the second event. And then let me explain why. So first of all, here's what we need to know. You have to recognize that this is an AND probability, and you have to recognize that because we're using because it's an AND probability in multiple trials, we're going to use the multiplication rule. So why is it an AND probability? It's because it's multiple trial, right? The probability of that the first selection is a student in class 3, and then the second trial, the second student is in class 3 as well. So we know we're going to use the multiplication rule. So we know so we have to look at, well, what's the probability? So the multiplication rule says that's the probability of event A times the probability of event B, given that event A has occurred, right? And it just happens to be that both of these events are class 3. It doesn't matter, right? So what is the probability that the first student is from class 3? So the first selection, how many different ways can I select the students from class 3? Well, there's 32 students, so that's how many different ways I can select the first student being from class 3 out of 155 students, right? Times. So again, we make a selection, we select the first student, and we don't replace it. We put the name on the side. So imagine we have a hat full of names. We make a selection, right? And then we place it on, let's say, like a table or something. And then we make the second selection. So what's the probability that the second student is from class 3, given that the first student is from class 3? Well, let's see. So how many different ways can we select a student from class 3? 31 ways, right? So why 31? It's because we made a selection in our first selection. We assumed that student was from class 3. So we're 1 less from class 3. And then over 154. Why 154? Is because we drew a name out in the first trial and we set it aside, so we're 1 less. So we're 1 less class 3. That's how we got the 31, and we're 1 less total. That's how we got the 154. So we're going to multiply this. We can multiply straight across. So we're going to go open parentheses, 32 times 31, close parentheses, and then we have 155 times 154, and then close parentheses there. Okay, so rounded to 4 decimal places, we get approximately 0.0416. Okay, now let's take a look at the second one. So the second problem says, find the probability of selecting 4 students from class 3. Assume selections are made without replacement. So it's also without replacement. So in this one, it's the probability that all 4 students are from class 3. Well, how can that happen if we get all 4 students from class 3? So that would be that the first selection that was made, the student was from class 3. The second selection, the student was from class 3. And then the third selection, the students from class 3. And then the fourth, the students from class 3. So this is a multiplication rule problem again, because we're dealing with, we can interpret this as and, right? Class 3 and then class 3 and then class 3 and then class 3 for each of the trials, right? So multiple trials and probability. We know we're going to multiply each of the probabilities. So the first one is the first fraction probability would be the probability that the first student is from class 3. So how many different ways can we select a student from class 3? Well, 32 ways, right? 32 out of over 155 times. And again, this is made without replacement. So we take a name out, we place it on the side, and we do not put that name back in, right? And then for the second selection, we're one less from class 3, so it's going to be 31 over 154. And again, 154 because we're one less total. For the third selection, there's now 30 names less. There's 30 names left that's from class 3, right? Over 153 because we're also one less total. And then for the fourth selection, it's going to be 29 over 152. All right. So let's go ahead and work that out on the calculator, see what we get there. So open parentheses. Okay, that's the numerator. Close it off. Divide by. Close the parentheses. So evaluate. So we get approximately 0.0015. Oops, sorry. 16. Okay, and now let's take a look at C. So C, we have the probability of selecting 4 students from class 3. Assume that the selections are made with replacement. Now, this is a different scenario. This is a different scenario because now, let me highlight it with a different color. But right now, we're dealing with replacement. Now, how does that change things? So we have the probability that the first student is from class 3, and then the second student, class 3, third student, class 3, and the fourth student is from class 3. So all of them are from class 3, right? This is the only way that we can get all 4 students from class 3 is if the first one and then the second and then the third and then the fourth students are all from class 3. But the difference with this problem is we're making the selection with replacement. Now, what does that mean? So that means the following. Well, first of all, we know we're going to use the multiplication rule. So the first number we're going to multiply is, we have to ask ourselves, well, what's the probability that the first student is from class 3? Well, there's 32 students out of 155, right? That's the probability that the first student is from class 3. So 32 different ways we can select a student from class 3 out of 155 students in the hat, right? Okay, but then we make the selection, we make our first selection, right? We make this first selection, and we don't place it back on, we don't place it on the table, or we don't set it aside. We take that and we replace it back into the hat, right? So that's what replacement means. You take out a student and then you put the student back into the hat and you shuffle it up and then you pick again, right? So now how does that change the second probability? It doesn't, right? So what's the probability of that the second student is from class 3? Well, it doesn't change anything. There's still 32 students. There's still 32 different ways we can select a student from class 3 because we took one, the first name we took out, we put it back in. So in the names or the number of names in class 3 and number of names total doesn't change over 155. Right? So take out a second student and then we replace it again, right? With each student we select, we put the name back in. And then for the third selection, third student, the fraction or the probability is the same as well, because again, we're making the selection with replacement. So then we get this fraction, we get this product right here. We get this product 32 over 155 times itself, and where it's going to show up 4 times. So we know we can write this as an exponent. So 32 over 155 raised to the 4th power. So take out the calculator. So here's how we're going to do it. We're going to open parentheses 32 over 155, and then we're going to close parentheses, and then we're going to raise that to the 5th power. Sorry, to the 4th power. So let's try that again. To the 4th power, and that's our answer. So we get approximately, I'm going to write it down here because I'm running out of room. So rounded to 4 decimal places, this is 0.0018. Okay. Okay, so that's how it's done with that. So again, this is a situation with replacement is where it's dependent, and question C or situation C is where it's independent because it's with replacement. And again, with replacement, the probabilities aren't affected after each event. So events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the others. So it's independent when it's with replacement because the probabilities aren't affected. That's why they don't change right after each trial. So question D, I'm going to let you guys do that as practice. Let's take a look at these other problems. So I've tallied up the columns and the rows to make things easier. If you guys remember, this is the same exact table that we had, frequency table, two-way frequency table that we used in the prior videos. So this is like the total number of orders from restaurant A, and then this is B, this is C, this is D, and so on, right? And if you add up all the orders, for example, if you add up all the orders from each of the restaurants, you get a total of 1109. Similarly, if we go across, this is the total number of accurate orders, and this is the total number of inaccurate orders. And if you also add those two up, right, the 973 plus the 136, you get the total number of orders as well. All right, so let's go ahead and answer these problems here. So for question A, it says, if 3 orders are randomly selected, find the probability of getting both from restaurant C. Assume the selections are made without replacement. So because it's without replacement, we know it's dependent, and the probabilities are going to change after each trial, right? It's going to be affected after each trial. So this is the probability that the first restaurant is from, again, there's 3 orders we're selecting. We make a selection. The only way we can get that, this should have been getting all from restaurant C because there's 3. So the only way we can get all of them from restaurant C is if we have the first one being from restaurant C, and then the second one being from restaurant C, and then the third being from restaurant C. So we know this is a multiplication rule because it's an and probability in multiple trials, right? We're selecting 3 orders. That's what makes it a multiple trial. All right, so that is the probability of the first one being from restaurant C times the probability of the second one being from restaurant C times the third one being from restaurant C. But then because it's independent, we have to consider the change in the probabilities after the first trial. So what is the probability that the first restaurant is from, or the first order is from restaurant C? So how many different ways can we select an order from restaurant C? Well, there's a total of 274 orders that we can choose from, right? That's how many different ways we can select the first order being from restaurant C out of 1,109 total orders times. What is the probability that the second order is from restaurant C? So how many different ways can we select an order, the second order being from restaurant C? Well, that's 273. Why is 373? because the selections are made without replacement. So we take the first one out and we don't put the selection back in, right? We put it aside. So now we're one less from restaurant C, and then we're also one less total. So that's going to be 1108. So the probability that the third order is from restaurant C, well, how many different ways can we select an order from restaurant C, given that the first two orders were already from restaurant C? Well, we're one less, so that's 272 over 1,107, right? So here, again, we're going to multiply straight across. So we're going to multiply straight across, open parentheses, 274 times 1109. Sorry. 274 times 273 times 272, and then close parentheses, that's my numerator there, divided by, open parentheses, 1109 times 1108 times 1107, close parentheses, and we get that. So rounding to 4 decimal places, the 4th decimal place is the 9 here, and the 5 here is going to increase the 9 to a 10, so that's going to be a 0 here, and we're going to carry the 1 to the next place value, so we're going to get 0.0150. All right, so that's going to be 0.0150. For the next question, 3 orders are randomly selected. Find the probability of getting, again, this is grammatically incorrect. This should have said all. So all from restaurant C. So same problem, but now it's with replacement. So we know that whenever it's with replacement, instead of diminishing 1 from the numerator and 1 from the denominator, it's just going to stay the same, right? There are 274 different ways we can select from restaurant C times 274 from restaurant C for the second selection times 274 from restaurant C. And nothing changes because after each selection, we're replacing it. So this is exactly how we're going to do it, right? So we're going to open up the parentheses, 274 divided by or over 1109, close parentheses, and then raise that to the 3rd power. Okay, so that's going to be 0.0151. So 0.0151. All right, so notice how they're very, very close. Whether it's with replacement or without replacement, the answers are very close. And sometimes, depending on where you round it to, you're going to get almost the same. You're going to get the same exact answer. So kind of keep that in the back of your head, because we're going to be talking about something in a bit that's related to that because they're so close. Number 2 is a little bit different, and I want you guys to pay attention to this one. So for example, so let's go ahead and read it. So we have a 6-sided die is rolled 2 times. Find the probability of rolling a 5 on the first roll, then rolling an odd number on the second roll. Okay, so we know we're looking at the probability that the first roll is a 5, and then the second roll is an odd number. Okay, so because this is multiple trials, right? Multiple trials means more than one trial. We have 2 trials here. And we know this is going to be a multiplication rule problem. So what is the probability that the first roll is a 5? How many different ways can we select? How many different ways can we get a 5 in a 6-sided die? Well, there's one way out of 6 total possible outcomes, right? The 6 possible outcomes are 1 through 6. And there's one way we can get a 5 times. Now, you might say, well, do I diminish it by 1 or not? Is this with replacement or without replacement? So notice how this does not say whether it's with or without replacement. But then if you think about it, if you roll a die, you can't take that number out and say, you can't take that number out, right? So you can think of this as with replacement because you can't take out a number. If you roll, like, let's say a 5, you can roll a 5 the next time because it's not as if the 5 doesn't exist after you roll the first time. So this is independent because you can think of it as equivalent to having a replacement. Okay, so what is the probability that of an odd number? How many different ways can we get an odd number? Well, there's 3 different ways, right? That's if we roll a 1, 3, or a 5. out of 6 possible outcomes. Okay, so this works out to be, we're going to multiply straight across, so that we're going to get 1 times 3, which is 3. And then in the denominator, we're going to get 6 times 6, which is 36. And we can just, if we want, we can turn this into a decimal. So rounded to 4 decimal places, that's going to be approximately 0.0833. Okay, so kind of going back to when I was when I had mentioned, notice how the first problem here with A and B here, the two answers are very, very similar. And I would say if you were to make 4 selections, like select 4 orders instead of 3, the more you select, the more orders you select, the more similar the answers are going to be. And again, if you round to, depending on what place value you round, you're going to get the same exact answer. But let's say instead of 3 orders, let's say we made 10 orders. We selected 10 orders here and 10 orders here. With the first problem here, without replacement, when we work this out, we would take this out 10 fractions, and then diminish 1 in the numerator and 1 in the denominator. Versus down here, where it's with replacement, all we have to do is we just take that 274 over 1109 and raise it to the 10th power. So the point is, the math is a lot easier when it's with replacement. When it's independent with replacement, right? That's with replacement indicates it's independent. The math is a lot easier. But then the answer are going to be very similar. So let me just show you what the answer you would get if you did 10 orders. So you would do the following. You would go in the numerator, you'd start with 274, right? And then diminish one after another. So you'd go 274 times 273 times 272, and then times 271, and you would keep going until you did it 10 times, right? And then you would divide by, the denominator would be 1109 times 1108 times 1107 times 1106, and you'd do that until you get 10 numbers, and it'd be cumbersome, right? The math itself is kind of cumbersome. Whereas over here, all you have to do is parentheses 274 over 1109, close parentheses, and then raise to the 10th power. And your answers would be very, 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 very similar. It would be exactly the same if you rounded to 4 decimal places. Again, this e to the negative 7, that tells me I'm going to move it 4 times to the left, which means I'm going to end up, if I round to 4 decimal places, it's essentially 0.0000. So because of that, we have this rule called the 5% guideline, because we recognize that the number one, the probabilities for when it's dependent and independent are very similar, but then the work that's involved in calculating is more difficult with replacement. When it's with replacement is more difficult versus with replacement. So we recognize that. So in certain situations, we're going to treat it as if it's with replacement or independent. I'm sorry. We're going to treat it as if it's independent, even though it's not independent. That's essentially what this is. So we call that the 5% guideline. So here's the condition in which we can apply that, or we can use that. So we have the following. It says, if the sample size or number of trials is no more than 5% of the population or total number of trials, treat the selection as being independent even when it's dependent due to without replacement. So let's take a look at this example, or a couple of examples, and try to understand when we can use or apply the 5% guideline. So number one, we have the following. It says, with one method of a procedure called acceptance sampling, a sample of items is randomly selected without replacement. So take note, it's without replacements, which mean we know that means it's going to be dependent, which means if we're actually trying to find the probability, the fractions are going to be affected because the probabilities are affected. So it's without replacement, and the entire batch is accepted if every item in the sample is not defective. So if every item is in the sample is not defective, the whole batch is going to be accepted. A company has just manufactured 1,706 blood glucose meters. 1363 are not defective. Okay, so that's what we have in our pool. So we can think of this as the pool or a population, right? So we have a population of 1706, and then 1363 are not defective. So let me make this circle a lot bigger. Okay, so we have this total. Okay, and then it says if 3 glucose meters are randomly selected for testing, so that's going to be our sample that we're going to use to test, what is the probability that the entire batch is accepted? So we select 3, that's our sample. Our sample consists of 3. What is the probability that the entire batch is accepted? How can that happen? How can we get the entire batch to be accepted? Well, according to the sampling method, the acceptance sampling method, every item in the sample has to be not defective. So that is the probability that the first one is not defective, and then the second one is not defective, and then the third one is not defective. So this is a multiplication rule problem where we're going to be multiplying the probability of the first one not being defective times the probability that the second one is not defective times the third one not being defective. And normally we would we would notice that it's without replacement, which means we're going to diminish the probabilities are going to be affected, right? But if we apply the 5% guideline, we can avoid that complicated math. We can avoid the complicated math, right? So we got to check. So how do we check? Well, we know that the sample size is 3, and we typically we denote the sample size with the letter lowercase n, right? So n is 3, and we have to ask ourselves: is 3 5% or less of the total population? Well, to figure that out, we would take 3 divided by the total, which is 1706. Right, so this is uppercase N. So uppercase N is used to denote the population. And let's see what we get. All right, so that's going to be 3 divided by 1706. And we get that. And as a percentage, we know we're going to multiply by 100 to get the percentage. This is approximately 0.18%, which is definitely less than 5%. Sorry, this is kind of messy. So it's definitely less than 5%, which means we can apply the 5% guideline, which says we're going to treat the selections as independent, even though it's dependent due to without replacement. So how does that affect things? So we know that the probability of getting the first one not defective is there's 1363 ways to select one that's not defective out of 1706. Times the second one is 1363 over 1706 times 1363 over 1706, and we get our answer, right? We can do the shortcut where we're going to write this as an exponent like this raised to the third power, and there's our answer. So approximately 0.5100. Now, the way I got that was The round off spot is the second 9 here. The 7 here is going to increase that to a 10, so that becomes a 0. And then the 1 gets added to this 9. 1 plus 9 is 0, so that becomes a 0. And then a 1 is added to the 0 here. That's how I got the 0.5100. Now, again, we're treating it like it's independent, even though it's not independent. It doesn't come handy for a small sample size, like just 3, right? We could have just diminished this and then diminished 1 here, diminished 1 here, diminished 1 here, and it's not going to be that bad of working it out. But imagine if you were selecting like 20 meters, the 5% guideline would be very helpful, right? And how do we test whether, let's say it was 20 glucose, how would we test whether it's less than 5%? No more than 5% means 5% or less, right? So we would go 20 divided by the total number of values, the total number of glucose, that'd be 1706. And that is less than 5%, right? Times 100 to get the percentage, that's 1.17%. So imagine had we had to work this out, not using the 5% guideline, we'd have to diminish 1 19 times because there's 20 trials, right? So it makes it a lot easier. So for a problem like this, so this is the final problem I'm going to cover. So a study conducted at a certain college shows that 72% of college graduates find a job in their chosen field within a year after graduation. Find the probability that 9 randomly selected graduates all find jobs in their chosen field within a year of graduating. Round to the nearest thousandths if necessary. So our sample here is 9, and we know that there's a lot of graduates each year, and definitely 9 graduates, selecting 9 graduates is less than 5%, right? Just kind of common sense. We know that there's a lot more than that, and 9 is a very small selection, and it's definitely less than 5%. So in that case, for a problem like this, where the probability is given to us as a percentage, we can just treat it like it's independent. Okay, so how would we get that all 9 of them are all graduate and find jobs in their chosen field? Well, that's the probability that the first one finds a job in their chosen field. And I'm going to use the uppercase letter J to represent somebody finding a job in their chosen field. And then the second one, and then the third one, and then ... the 9th person. And then we know that this is the multiplication rule because it's multiple trials, right? So this is going to be the probability that the first one finds a job in their chosen field times the second person finds the probability that the second person finds a job in the chosen field 9 times. So and we know that we're going to figure out that probability, or use that probability and raise it to the 9th power, right? So what is the probability that the first person graduate finds a job in their chosen field? Well, let's see. We're going to use this percentage from this study, which says 72% of school graduates find a job in their chosen field. So we're going to put that as 0.72 times, right, times 0.72 times ... 9 of them, 0.72. So that's going to be 0.72 raised to the 9th power, which is going to give us the following. So let's go ahead and work that out. So that's going to be 0.72 raised to the 9th power, which gives us that. So approximately 0.0520. Okay, so hopefully you guys found that lecture helpful. Again, if you have any questions, always feel free to reach out.